Hi guys, it's Robbie Wyness here today. Today I wanted to show you guys how to complete this water equivalent calculation. If we look at the syllabus for second class, you'll see that water equivalent is one of the topics that you guys need to know how to understand. So if we get into this calculation, it is determine the quantity of heat required to increase temperature of the water in cobalt calorimeter 35 degrees Celsius. The mass of the cobalt calorimeter is 0.34 kilograms and is filled with 0.8 kilograms of water at 12 degrees Celsius. The specific heat of cobalt is 0.402 kilojoules per kilogram Celsius, and the specific heat of water is 4.183 kilojoules per kilogram Celsius. So the first thing I always like to do is write the equation that we're going to use to solve the problem. So the equation is the specific heat equation. So it is Q in kilojoules. Let's make this pen a little smaller. Equals our mass in kilograms times our specific heat in kilojoules per kilogram Celsius times our T2 minus T1. So that's our temperature rise or temperature decrease. Step number 2, I like to define all the variables. So the first one is Q. That's our quantity of heat added. That's one of our unknowns. Another one of our unknowns that we'll have to determine is the water equivalent of the cobalt calorimeter. So we could go, I guess we'll just do QWE for water equivalent. So water equivalent of cobalt calorimeter equals unknown. We have our mass of the cobalt calorimeter, which is, let's say, MC. And that is 0.34 kilograms. We have the mass of the water. We can say that's MW. And that's 0.8 kilograms. We have the specific heat of cobalt. So we'll just say that's CC. So the specific heat of cobalt is in kilojoules per kilogram Celsius, and that's 0.402 kilojoules per kilogram Celsius. We have the specific heat of water. So specific, excuse me, specific heat of water, that's in kilojoules per kilogram Celsius, and that's 4.183 kilojoules per kilogram Celsius. We have our T1, that's our initial temperature. And that's in degrees Celsius, and that's 12 degrees Celsius. And we have our T2, that's our final temperature. which is in degrees Celsius, and that's 35 degrees Celsius. So step number 3 out of our 5-step process is state your assumptions. So we'll assume that while the quantity of heat that's required to increase the temperature from 12 degrees to 35 degrees, none of that heat that's applied to the cobalt calorimeter or the water is lost to the surroundings. So we'll say none of the heat is lost to the surroundings. So step number 4, which is the solution. We want to make sure we show all our steps, and we'll check the units in each step. So the formula we're going to use to solve this is the one we wrote above. So it's Q in kilojoules equals our mass in kilograms times our specific heat in kilojoules per kilogram per degree times our temperature rise. So it's T2 minus T1 in degrees Celsius. So we got to first of all determine the water equivalent of the cobalt calorimeter. So to get that, we go mass water. So the water equivalent equals the mass of the cobalt calorimeter times the specific heat of the cobalt divided by the specific heat of water. So we put in our variables. The mass of our cobalt was 0.34 kilograms. The specific heat of cobalt was 0.402 kilojoules per kilogram Celsius divided by the specific heat of water, which is 4.183 kilojoules per kilogram Celsius. So in the numerator and denominator, these variables are going to cancel out. If you divide 0.402 by 4.183, that should give you 0.0961. And if you times 0.34 kilograms by 0.0961, that'll give you a water equivalent of 0.0327 kilograms. So that was one of our unknowns, so I always like to just write it out. So the water equivalent of the cobalt calorimeter is 0.0327. So to 7 kilograms. So that determines the water equivalent, but we still need to determine the quantity of heat required to increase the temperature of the water and the cobalt calorimeter. So to do that, once again we'll use the Q in kilojoules equals our mass kilograms times our specific heat in kilojoules per kilogram per degree times our temperature rise, so T2 minus T1 degrees Celsius. So we put in our variables. Whoops, I'll have to back up here. I'll run out of room. So if we put in our variables, we'll have the mass of the water, so 0.8 kilograms plus 0.0327 kilograms times the specific heat of water, so 4.183 kilojoules per kilogram Celsius times the temperature rise, so our T2 was 35 degrees Celsius and our T1 was 12 degrees Celsius. If we do within the brackets now, so 0.8 plus 0.0327, that'll give us 0.8327 kilograms. So 0.8327 kilograms times our specific heat of water, so 4.183 kilojoules per kilogram Celsius, and then times our temperature rise, so 35 minus 12, that'll give us 23 degrees Celsius. If we cancel out what's in the variables that are in the numerator and the denominator, so the degrees Celsius cancel out, kilograms cancel out, and we're left with kilojoules. So if you times 0.8327 times 4.183 times 23, that'll give you a quantity of heat added of 80.11 or 11 kilojoules. So for step number 5, always state your final answer. So the heat required to increase the temperature of the water and the cobalt calorimeter from 12 degrees to 35 degrees is 80.11 kilojoules. So if you guys like these questions, as with the previous ones, we've included there'll be a link below where you can download this kind of workbook we have. It actually goes through like what is the water equivalent of a particular mass of substance, the equation, the formula variables. It has an extra practice question here. It goes into a little more detail of how we actually get to the water equivalent equals the mass of, in this case, antinomy, or the specific heat to antinomy in water. It shows you step by step how you can get there. It also has the question we just did. It's typed out and a little nicer. So if you guys want to download that, you can work through those along with the specific heat and so far I guess we've covered temperature scales, absolute temperature, units of heat, the specific heat, and the water equivalent. So if you guys download those workbooks and work on those, definitely help you guys learn the material. And then the video coming up next, that'll be sensible and latent heat mixtures. So if you guys like these type of videos, feel free to hit the like button below, subscribe to the channel. We're uploading almost 2 videos a week right now. We're on pace, and we'll talk to you guys in the next video.